and none other than Karel, Alfonso, Sague, and Rashmi, Shamsundar. Together, they will take us behind the scene of Cash App journey.
So today we are standing at the forefront of a revolution in data streaming. If you go back many years ago, like since mid-2000s is when stream processing was emerged as an area, critical area of focus. And until then, batch processing was more prevalent because it was more reliable. Since then, the stream processing frameworks have been innovating and evolving to handle unprecedented volumes of data. This has set the stage for the modern day and sophisticated frameworks like Flink or Kafka Streams or even Apache Storm and many others. Our own journey at Cash App of stream processing, starting from humble beginnings to the adoption of the most powerful framework like Flink, has been exhilarating. And that's exactly what we are here to share. Mai's already introduced us, so I'll skip this. Let me talk a little about Cash App, who we are. Cash App is a part of Block. So Cash started as a way to send money between two people. In that regard, it's a peer-to-peer money transfer app. And since then, we're not just a peer-to-peer system anymore, and we've moved way beyond that, adding a whole suite of financial products like cash cards, direct deposits, Bitcoin, investing, taxes, and many more. We're predominantly in the US, which is why you wouldn't have heard about us. And we provide economic empowerment to our customers by serving the underbanked especially. So Cash App's architecture is pretty complicated, which I can't cover in one slide. But if I should say it this way, Cash evolved from a couple of monoliths to a large number of services. These services are communicating with each other, yes, via synchronous RPC calls, but predominantly via an eventing backbone, which is built on top of Kafka. And these services are sending huge volumes of data related to payment, card transactions, identity information, or customer-related information, and many others. And the services who are using this information and consuming this data are using it for fraud detection, machine learning, reporting under reconciliation, or even data warehousing solutions, just to name a few. So with all these use cases that we had, we wanted to implement stream processing now. And there were so many other solutions in the market. And our naive solution was to implement some services where there would be consumers of Kafka, pick up the data from Kafka and do some kind of transformation, processing, put it into some data store, and then some other services would pick this data up, do more enrichment, and then put it into some other final data store where the destination would be. And we quickly realized that this was sufficiently complicated, an ad hoc implementation, and was not even half as efficient as modern-day stream processing solutions would provide. So after considerable evaluations of several platforms that were around, we realized Flink was the right choice for us. Flink it can be used to build real-time data products. It's a very powerful framework that can connect, enrich, and process the data. It provides once-only processing semantics, like exactly once. It has an active community and a supportive community so that it's very easy to get help from. And it has a unified architecture for both batching and stream processing. So all this flexibility that we got made it appropriate for the use cases that we had. How many of you here have used Flink or heard about Flink? All right, quite a few, but not as many. For the rest of you who are not familiar with Flink, here's a basic introduction. So just like Kafka is the de facto for data streaming, real-time data streaming, Flink has become the de facto stream processing engine. And it wasn't the case all this while, it's been the case since the past few years. What separates Flink from other equivalent technologies is these 4 areas that form the foundations of Apache Flink: streaming, state, time, and snapshot. We'll be diving into each one quickly now. So Flink is a true real-time data stream processing engine. Streams are a sequence of events. They can be bounded or unbounded. So events can be something like, for our use case, they were like payment events or card transaction events, but simply they could even be like number of button clicks on a web page. So bounded stream has a start and an end, a begin and an end. Processing bounded stream is called batch processing. You must have seen like daily cron jobs or like daily or an hourly jobs. And unbounded streams are continuous and they extend indefinitely into the future. Streams always flow from source to sink. And these sources and sinks can be messaging platforms or even files or databases. So whether it is a batch job or a streaming job, Flink job has, the heart of a Flink application is its job topology, which is a series of operations, like you could think of the source, which is pulling the data from Kafka and doing some kind of filtering. There's some aggregation. There's another operation doing aggregation, and then finally putting the data into sync. Operations like simple filtering do not need to store any kind of state. They need not. But more complicated operations like deduplication of events or even storing aggregation count, they need to store the state. And to achieve high performance, Flink stores the state locally in its node, and it also pushes the state to remote location, like a distributed file system like HDFS or an S3. And at Cash App, we have our local state in RocksDB, and we do push the state to the remote location periodically. And this concept is called as checkpointing. We'll be talking more about this very soon.
Excellent. So let's talk about how Flink manages the notion of time. And this is an important concept that you have to take into account once you are working in the stream processing area. So the first one is, how do you gather the time information for you to do sensible computations and implement your business logic? You have two main ones that we can talk about. One is processing time. The other one is called event time. So Flink is a distributed, stateful data processing engine. And this means that this directed acyclic graph that Rashmi mentioned will be running distributed operationally when you look at it in the actual deployment. So the operators are going to run distributed, and when you're using processing time as a notion of time to build your application logic, it's going to depend on the wall clock on the nodes where each of the operators are running. This is quite simple in terms of implementing the logic, but if you are familiar with distributed systems, you know that the time in each of the nodes can differ, and this could lead to non-deterministic results. So Flink also allows you to get the time from the event, which is the time when the event actually happens. So for instance, if the event is being generated from an IoT device or some other system, it's the time when the event actually occurred. And then you can use that within your application. We're going to show a demo very shortly. The next thing is, and this is somewhat related to time, so we have an unbounded stream of events. So we know doing a batch processing, where you know that you're starting, let's say, on daily or hourly, and you know the start and the end of the data that you're going to process. You have an unbounded stream of events. So to do some sensible logic, I mean, you can actually do a rolling aggregate or some operation on an unbounded stream of events, but the majority of the use cases use some mechanism to define a boundary between, could be based on time or the amount of events, so that you can do some computation. So with Apache Flink, you can define different types of boundaries, and they're called windows. And the main ones that we have listed here, tumbling window defines a size. Say you can look at the events of the last 5 minutes, and you can do some computation to implement your logic, and then you move to the next 5 minutes window. Or you can have a sliding window, which is The tumbling window is a special case of the sliding window. So you still define a size in terms of time, and it slides in some other time parameter as well. So that is the slide size. And the advantage of this one is that for some use cases, it's valuable to get the result of the computation as soon as possible. So if you have a tumbling window, you get your computation when the window ends, while you can look at, let's say, the amount of cars that are going through a checkpoint over the last minute, for instance, and you get it every second or something like that, the result is going to be output in a timely manner. So that's the value of using sliding window, and is depending on use cases. And then you have session windows. It gives you the ability to define inactivity gaps in the event stream that is coming, and then basing the computation on that inactivity gap. Another important feature that Flink gives you, and it's present in other stream processing engines, is the concept of watermarks. And this is relevant when you're using event time for your computations. The watermarks allows you to decide at which point you're gonna make progress in your stream processing logic and decide, okay, I've seen all the events that I was hoping to see up to a specific time. And these watermarks, in the case of Flink, they are inserted as part of the event streams. In the example that I'm going to show, for instance, if you're using the Kafka connector, the Kafka source connector in Flink will inject periodically watermarks based on event times. We'll show an example shortly. But this allows you to, when you're using event time, when, for instance, if you go back to the window, when do you close the window? And it's taken out of the event, and you can say, the out of orderness could be, let's say, 5 minutes, and after that, the window will close, and there are some other features that you can use to decide what to do, either output the computation of the window or wait a little bit more, because there could be unordered events, which is quite common, especially if it's coming from IoT devices. So that's what watermarks gives you. All this, we are trying to communicate. It's like a really concise overview. All the Flink documentation goes deep into detail, but yeah, it can get quite complicated. But these are important concepts to take into account when you're thinking about time in stream processing applications. The other one is snapshots. That's the fourth one that we mentioned. Flink being a distributed system, if you recall the slide, for some operators, if you're doing some aggregates or counting, there's some other operators that manage state. Flink keeps the state locally in the node where the application is running. But then what do you do with that local state? So in Flink, they have the concept of snapshots, and it's implemented in two ways. The local state that resides in the nodes where the operators are running gets checkpointed, which is a mechanism to do backups of that state to a distributed object storage, or could be HDFS, a distributed file system. And this is the way that Flink implements fault tolerance. So at any point, you can go and kill one of the nodes or the processes, the whole job will fail, and then it will restart from the latest checkpoint automatically. And then you have save points, which is kind of similar to checkpoints, but they're used when you want to deploy your application. So you can manually take a save point or using the API provided by Flink, and when you deploy the new version, start from the latest save point. So with all these concepts, to give you a better understanding of what Flink looks like, I'll show you a hypothetical. I'm going to use this, a hypothetical fraud detection system simulating users doing some payments, and the logic that we're going to implement, this is a heuristic if we have this, also arbitrary, by the way. So if in the lapse of 30 minutes, someone has done more than 3 payments, it will be identified as fraudulent. And same if in that time, it's an or, if in that time the amount exceeds $3,000, it will be detected as fraudulent. So I have this demo is actually in GitHub. Is using Docker Compose with Kafka and Flink. We have it running there for most of the part. All this has already been set up for this demo. So you can see there a Kafka broker, job manager, task manager. These are components for Flink, and then we have a SQL client in there. And I've set up some topics in here where we're going to use the payment events topic, where we're going to simulate the transactions coming through Kafka from one of our services, and then if it's detected as fraudulent, it will be sent to this Kafka topic. After that, your imagination can flow free. You can do trigger alerts. You can revert transactions, etc. This is running already in Docker, and with Flink you can have access to a UI that they provide. I'll make this one bigger, and you can see there the application listed, and you sort of can see a representation of the DAG. So this is, I show you the code briefly now, and it's telling you a few metrics there that the application is running. And I've already run some load. I put already some simulated payments in Kafka, and then you can show the fraudulent payments. And it has already, the Flink job has detected already some payments that are fraudulent. In this case, it just has the customer ID, some identifier for the customer, the amount, the time window. I'm using the milliseconds long value in this case, and the location which I've set up in there. So back to the presentation. I show you in the anatomy of a Flink code. And this is not to, I guess, there's a bit of code here, and always show, sorry, I wanna show the presentation mode. View presentation. So in Flink, the main concepts and things that you have to represent in code is your sources for the systems that you're going to interact with. In this case, it's going from Kafka to Kafka, and Flink has connector for really quite a few of the more mainstream systems that we're using right now. So you have to set up your topic, and whether you're going to start from the earliest offset of the Kafka topic. And then an important thing is Flink has to deserialize those messages from Kafka and serialize them back into Kafka when it's publishing it. So you have to have all that into account. All this is using Kotlin as a language, but Flink can be implemented in Java and Python as well. This particular example uses protobuf just because that's what we use a cache app mostly. And you also have to register the protobuf serializer. So similar to what we do with, I'll show you in the code, with distributed services. When you get an object from a client, we turn that object internally into our own representation of the data, do the computation, and then turn it into the object that we're going to put in Kafka. So this is the serializers that you see here listed. And this is how you define the watermark that I was just talking about. We're saying that we're going to have 1 minute, and that will be the out of orderness that we are, at least for this example, willing to accept for events. So that, for instance, when we have the window, we can decide when the window closes. So the way you define the application, this is very simple. So we are transforming here to our internal structure, and then we are partitioning the stream by the sender ID. Then we define a window that says it's going to be a tumbling window of 30 minutes, and we're going to allow lateness of 30 seconds. So that one, what it says is, once the watermark passes and Flink decides it's time to close the window, we're also willing to wait 30 seconds more for some potential events that will be out of order. And this is something that we cannot, unfortunately, we cannot go away from. So when you're doing stream processing and handling events, you have to realize, I guess it's depending on use case, that you're going to get events out of order. It's not represented in the code here, but once the out of orderness time passes, the event gets dropped. So you can have data loss. For that, Flink gives you other features such as side outputs, I think is how they call it, and you can say anything that didn't get included into the window because it was late, put it into this other topic, and then you can have some administration process to decide what to do with those events. And then, yeah, once you have the window will output a new stream that you can filter on the fraudulent payments events and then map it into the protobuf that we're going to put into Kafka and send it over to Kafka. So this is using code. Flink gives you also, and this is where if you look at the latest as-a-service companies that are building on Flink, such as Confluent and Decodable, they're all leveraging Flink SQL, which is something that people have realized, yes, as software engineers, we are happy to write code, but there are other users of these data processing platforms, like data scientists and analysts that are more familiar with SQL. So this is a big area right now. So will the code be simpler in SQL? Flink SQL also have its own connectors. And in this case, what I'm doing here is defining the payments table in Flink SQL. And you can see the connector for Kafka and similar configuration that we had in the code, including the brokers, the earliest offset. And it's very simple to define that we're going to be use the protobuf format in this case. The only thing I have to specify here is the payment event protobuf that I'm using in this example. So that's a source table. Then you define the sync table where the data is going to go to, which is going to go to Kafka. And again, you define it in similar way. Actually, the other one is that in the source, you can define the watermark. In this case, because in Flink SQL, I'm using the created at, it's a big int, I have to convert it into a timestamp, so I'm having a synthetic column there to do that, and I'm still defining the watermark to be 1 minute out of orderness, and I'm willing to have for the events. And this is the core logic in here. So it still requires some knowledge and understanding of Flink SQL. As you can see, this is not standard SQL completely. There's some concepts here that are not in the SQL standard, like Tumble, to implement a tumbling window. But you can implement the logic relatively easy. If you're familiar with SQL, you can say that I want to get from the sender ID, I want to add the total amount, and I'm going to also count the number of transactions for that sender. And these last two lines is just defining the start and end time of the window. And then we're going to say, we're going to do a tumble window of an interval of 30 minutes. And then I'm going to group by the sender ID, because of this logic is per customer in that window, in the window start and window end. And if either or the total amount or the number of transactions is greater than 3,000 or 3 respectively, then it will be sent to this Kafka topic here. So I'm inserting into the fraudulent payments table. So that's how it is with SQL. And it's something that I think most of the companies, as I mentioned, are moving towards. So we see a bit more of Flink SQL, and we're certainly moving with that approach as well in Cash App. So overall, from a programming model perspective, Flink gives you a layered API that goes from the lower level of abstraction up to Flink SQL, which is the highest level of abstraction. If at any point you need to do some really custom solution, which I imagine there will be use cases out there for, you can go all the way down to process functions where you have to implement your own windowing strategy and how things are going to trigger and all that. So it can get a bit more complicated. But for the most part, we found that using the data stream API and the Flink SQL API is suffices for most of our use cases. The table API is similar to Flink SQL, it's just that you should write it in code. So you'll be writing Java, Python, or Kotlin code and writing SQL inside your code. So let's have a look at the runtime architecture for Flink now.
Awesome. Thanks, Karel. That was a great demo. I wouldn't have dared to do a live demo. Yeah, we saw the internals and working of the Flink application and then the anatomy of a Flink app, what the code looks like and all that. I would definitely choose Flink SQL, like less code is better. So let's zoom out a little and see what the architecture of the Flink application looks like, yeah? So when we write the Flink application, whether we use the Java API, whether we use SQL, that becomes the client, and when we execute the program or the application, it creates a job graph, and it submits the job graph to the job manager. Now, what the job manager now does is it's responsible for finding the resources that are required to run this application and schedule the job. So if you see in this diagram where you see one job manager, and we have two task managers as an example, and the task managers have several task slots. Each task slot is going to run one parallel instance of the job. And once the job is running, the job manager is now responsible to kind of coordinate the activities inside the Flink cluster, like starting and stopping the task managers, like triggering checkpoints like we talked about earlier, which is like taking snapshots, periodical snapshots, and even like tearing down canceling the tasks and everything. And even like responsible for putting the results, like sending the results back to the client. So that constant communication. Job manager is like looking after everything. The task managers, on the other hand, are also talking amongst themselves. Like there's a constant communication there. So when you saw the code and demonstration and all the code and the Flink SQL, everything, you'd be wondering, it's like a lot of things, a lot of moving parts. Yes, Flink is complex, and onboarding any new technology is a difficult endeavor for any organization, especially if it's like something like Flink. If you were there for the morning's keynote from Scott, that kind of struck a lot of chords because it is very similar and very aligned to what we think in our organization for platform teams. I really loved that talk, by the way. We are a platform team. We are in DataPlat in the Cache umbrella. And what's important for us is to develop a self-service tool, empower our product engineers, provide a self-serve tool for them, which is like reliable, secure, most importantly, saves their time, which is providing developer velocity, increasing developer velocity, and increasing their productivity. So we have a set of guiding principles at Cache that we used for developing Flink applications as well, by bootstrapping, putting bootstrapping around development of Flink applications, making provisioning simpler, and making operating them easier. So let's talk about what goes on in building a Flink application from scratch at Cache. I would like to take it as, talk about it as 4 layers or 4 components to this. There's libraries, and there's an app template, there's a CLI tool, and a CI/CD pipeline that we provide. So the Cache Flink libraries is a thin layer, and it's a collection of all the Flink libraries that are required in order to make building Flink applications easier. So via this layer, we provide libraries for like serializing, deserializing that Karel was talking about earlier, all the code that you saw, testing, metrics, even feature flagging for rolling out purposes. We also expose libraries for multiple Flink versions so that the engineers can now choose the library matching their Flink application. The next is the app template. Like the name suggests, it's a scaffolding around Flink application. The engineers now can use a simple 1-line command and create a Flink application from scratch within like 5-10 minutes. What this gives them is a bare bones application which has a Kafka as a source and Kafka sync or an S3 sync, depending on the use case. We have a lot of use cases in Cache around Kafka, so that's what we provide by default. And it is very easily customizable. We provide all the documentation. We provide guidance for the teams to do that, and support for the team to do that. And once they have an application ready, they also get access roles and all the access controls and roles that are required in order to make this application deployable or runnable in the next steps. This is good because the engineers now don't need to write Flink boilerplate code. Now they can just write their business logic, whatever transformation that is required, and they have everything else ready for them. CLI tool is another set of utilities that we provide to facilitate working with Flink application. It's a simple tool. It provides a mechanism to work around, like manage application lifecycle, like creating, destroying, and even if they want to get access to the logs, they can just use the CLI tool and open up the logs for their application easily. We also help creating custom resources like AWS resources or Kubernetes resources. That's where our application finally gets deployed. So they can use the CLI tool for that. And the last but most important one is also the CI/CD pipeline. We use BuildKite at Cache for CI/CD purposes. So we stuck with the same process for Flink applications as well to keep the familiarity for the engineers. A default, like using the app template when they create a new Flink application, they also get the provisions for creating a BuildKite pipeline very easily. So a bare bones pipeline will look like having a build, a test step, release the artifact to S3 buckets, and then the deploy step deploys the application, the Flink application, onto Kubernetes.
Excellent. So let's take a look at what happens in this last stage of the CI/CD pipeline. Again, going back to that presentation this morning, as a platform team, one of the main drivers is to simplify the process of not only building the applications and all these other libraries to make it easier, but then how do you deploy the application? So for most of our infrastructure, not only for Apache Flink, we already have a mechanism that is in-house built. It uses a common language. I guess you're familiar with Terraform, uses a HCL, which stands for HashiCorp configuration language. So we decided to implement most of our infrastructure using this HCL language. And for Flink, we did the same. So this is an application declarative manifest that we have. For the most part, we provide, to get started, sensible defaults. And in this case, this is as simple as you can get for a Flink application, where you have to specify the yard tag or the SHA, which is the output of the build from the CI pipeline, the version of the Flink system that you're using, and the desired state of your application. So using this manifest, you can change the desired state to cancel or running to stop the application or get it started. And then, as you know, so we deploy to Kubernetes, so we have some other extra configuration that we allow them to customize, such as the CPU and memory resources that they're going to use, although they're not shown in this manifest. So this manifest is used we have an in-house build tool. It's built in Golang, but it's a very thin abstraction on top of Terraform, Helm, and Ververica is the solution that we use to run Apache Flink. There are other solutions out there, as I mentioned. There's a Confluent Flink solution. There's the Codable KDA from AWS. We use Ververica in Kubernetes. And the provisioner talks to Terraform, Helm, and the APIs provided by Ververica to create all the required resources that you need to have a functioning Flink application in AWS and mostly Kubernetes. So the next thing, once the application is deployed, and this deploy, by the way, happens we do allow manual deployments, but all this happens automatically. That provisioner gets invoked directly in the CI/CD pipeline, and then the application gets deployed in Kubernetes. And the next thing is, okay, now you need to have visibility of how your application is running. And this is, as we mentioned, Flink is a distributed system. It's a synonym for complexity. There's quite a few metrics that you need to understand so that you know that the application is working properly. So for instance, with Kafka, we need to look at the consumer lag to make sure that we have the resources required to catch up with whatever the throughput is flowing through the Kafka topics. So we have defined these dashboards in Datadog, which is the observability tool that we use. And all this is also set up by default when you provision your application as well. So we have the Flink-specific metrics as well as application-specific metrics there in the dashboard. But our engineers don't have to build these dashboards. They are already created for them. So let's look at some of the challenges that we had.
Yeah, we laugh because if you're working with Flink, you'll know that it's not an easy framework to grasp. Like there will be a steep learning curve. And we did definitely face a lot of challenges when we were learning as well. So we were a team of 6 people, like working on Flink and onboarding Flink. That was new to us as well. So a lot of challenges that we faced were around state management and handling large states or upgrades. What happens like when there's backward compatibility? There was even like deployment challenges and then dealing with downtime. And quite a few others as well. And in the interest of time, I will not talk about every challenge. Otherwise, we will be here all day talking about Flink. Let's probably talk about some things that kind of interested us and was insightful. Scaling for traffic was an interesting problem for us because at Cache, like we don't have a predictable traffic because there's on-peak, off-peak traffic to consider. And it's always unpredictable depending on how the payments, activity, customers, everything goes on. So when our Flink applications are under load, we need to definitely scale them up in some cases. In some other cases, evaluate what is happening with the Flink application if it's slower. So if we provided more resources to our Flink applications, like say, give it more memory or throw more CPUs at it, we would not be solving the right problem. Sometimes it would be like over-provisioning this application and then wasting a lot of resources. So doing more harm than good. And then if you just right provision them or under provision them, then sometimes the application could be failing or it'll slow down drastically because it will not be able to take the load. So that will also not be good. The ideal scenario or the ideal solution here is to adopt auto-scaling. So with Flink, Flink supports auto-scaling using reactive scaling, in the reactive mode. Solution providers like cloud providers like AWS, Kinesis Data Analytics, I'm not sure if you're familiar, they adopt AWS's auto-scaling, integrate with that, and provide auto-scaling. Ververica, what Karel was talking about, one of the other providers, they use their own solution. They have their own solution for doing auto-scaling, and they call it Autopilot. That is exactly what we are using in Cache, using Autopilot and trying to scale the Flink applications. We're still experimenting with it, by the way, so we don't have it 100% working. It's in progress. The latest version of Flink also supports. Oh yeah, before I move on to the latest version, the problem with auto-scaling, or not exactly the problem, like it comes with downtime when you're scaling your Flink applications, and sometimes downtime is not good for many cases. But the latest version of Flink also does scaling in place, so which doesn't have to involve pulling down your application and like restarting it. So that's about auto-scaling.
Excellent. So the last challenge we want to talk about is deployments. And we're all familiar with blue-green deployments when we deploy applications where you have your production application running and you want to deploy a new version, which is your blue environment. In Flink, unfortunately, we can't do that. You need to stop your job and then deploy the new application. So we needed to find a way to get confidence on, even with all the testing that we have in the pipeline, until it's running really, then you don't know. Sometimes we have poison events. There's a few things that happen we didn't get a chance to cover here, so we needed a way to run this in production. The way we do it is we run 2 different Flink applications. One is the green one cluster, which is always running, and then we have a blue one where we deploy the new shaft while the old version is running. We wait for Flink to trigger the first checkpoint. This happens on schedule, and you can configure how frequent the checkpoints should happen. And once the checkpoint occurs and we don't have errors in production, then we can turn off the blue environment and say, okay, it's safe to deploy the green environment. The blue environment doesn't write to the sink, so it's taking shadow traffic and just making sure that we can take a checkpoint and there are no errors in there. So pretty much that's, as far as we could do in that case, there's no solution at the moment for blue-green deployment, and any deployment requires a downtime for your job. So we've tried to cover, which is very challenging in the time of 50 minutes in this presentation, introducing how we are using stream processing, especially with Apache Flink. The message we would like you to stay with you. So stream processing, the way we've seen the use cases at Cache, and you have to make sure, especially if you're using Flink or some of the other modern platforms, that you're using for the right purpose, the right use case. So we have situations where our data warehouse at the beginning, 6 years ago, we will have data that was uploaded from the operational databases on a daily basis or probably a few hours. So when we had situations that required critical customer support or some action, we couldn't use the data warehouse because we had state data, we didn't have the latest data. So our largest Flink pipeline right now is implementing Apache Flink, and it provides streaming data directly into our data warehouse for all the Kafka topics that are relevant for our topics, which means that whenever we want, we can use the data warehouse now to build data products and applications based on real-time data. We don't have to upset, which used to happen in the past as well, our operational databases. You don't want to be running queries directly there. Even if you hit the replica endpoints as well, it can cause issue because we have services already using the reader endpoints. So try to use it for the right use case. Maybe if you need a daily process, doesn't make sense to have a window of 1 day. It is possible, but then you have to take into account that state that can grow a bit large depending on what you're doing. So rolling out Flink requires expertise. We've deployed more complex systems at Cache App in data platform. Flink, if you look at the Kubernetes deployment, is not too complex, but it's still a distributed system. As you can see, it has local state and this checkpointing or the recovery time. It requires expertise. So going back to Scott Shaw's presentation this morning, you need the platform thinking approach and the developer experience. Otherwise, it's probably not going to be successful. Even with all the things that we put in place, our on-call and support gets hammered every time with requests, especially lack of expertise and understanding of the programming model. You need to pay attention to the availability SLOs for your application as well. You know, you need to turn off your job for deployment, the same for scaling. When you have to scale a job manually until you deploy the latest versions of Flink that are aiming to do in-place scaling, you will have downtime. So we recommend, at least if you want to get started, to look at some more non-critical customer-facing solutions to get started there. And then Flink has many other exciting features we haven't talked about here, like stateful functions to write distributed serverless functions that use leverage streaming. You have complex event processing to determine patterns in the events. You don't have to write the code to simulate that. It's already included in that library. And if you want to learn more, well, there's the Flink open source documentation is quite good. Confluent has now jumped on Flink. So they used to support Kafka streams, and now they are putting all the weight on Apache Flink. They have really good introductory resources there as well that you can see. And feel free to interact with the demo that I have there. There's plenty out there in GitHub as well. So that's pretty much what we have for you today. Thank you very much.